Okay, so we finished talking last time. We did some real basic stuff. We defined stress and strain, and we talked about what state variables are. And so what we're going to do today is talk about applications of that. We're going to start off by talking about transformations of stress, and then we're going to look at Mohr circle, which is a two-dimensional way to look at stress. And it's a very, the Mohr circle is a really nice method for learning about behaviors, because it's something it's visual, it's easy to do, you can do it qualitatively and show things, and you can also do it quantitatively and actually calculate stuff. And then, I forgot what the last piece of today's thing is, but we'll do that in the second half. So the first thing we're going to start talking about are stress transforms. So we talked about state variables last time, and this time we're going to specifically talk about the state of stress. And we'll spend a little more time talking about that conceptually at the beginning. So this concept of a state of stress is really important. And the concept of a state of stress is different than the values of normal stress and shear stress in some arbitrary coordinate system. It's kind of like a broader concept. So I want to make sure when you're done today, you actually can explain what the concept of a state of stress is. And then we're going to talk about different stress and strain models that we use in soils, and you need to be able to explain the relationship between stress, strain in any arbitrary coordinate system. And finally, we're going to be talking about, we're going to derive almost everything in this class in 2 dimensions, and then just kind of do an intuitive transfer into 3 dimensions. So I'm not going to sit there and derive stuff in 3 dimensions because it's too hard, and there's just so much math that you lose understanding. But we're going to talk about this concept of a stress tensor and the invariance to the stress tensor, and you need to be able to you need to be able to understand that stuff. So let's talk about this concept of the state of stress. And so a good model of this is, let's talk about a slope, and let's assume that at some point below that slope A, we're going to want to know the behavior at A because we're looking at a slope stability problem. Well, so here's my little element at A. And I might initially have this thing defined in, an XY coordinate system, because that's, the way things start. Gravity points down, ground's kind of level. So I might initially, we're going to drill sampling borings that are going to go straight down. So the initial coordinate system that we're going to be interested in is the XY coordinate system. And in that system, we're going to have a normal stress, sigma z, coming down. There's going to be a shear stress Zx there. The stresses on the bottom are going to be the same and opposite. And on the sides, we're going to have a sigma x. And there's going to be a tau xz. And the values of tau xz is going to be the same as tau zx here. It has to be for equilibrium, right? If they're not the same, then this little square is going to be spinning. So we're going to have that. We're going to have that coordinate system that might be a very reasonable coordinate system to start off with, because that's kind of our natural coordinate system. But if I was looking at this thing as a slope stability problem, I might actually be more interested in this coordinate system that's parallel to the slope. Or it could be that I'm looking at a slip surface that runs through that point like that. I'm more interested in that particular coordinate system. So I have to be able to translate the values from one system to the other. But the soil at point A doesn't know the difference. The soil at point A doesn't know x, y, z, 1, 2. It doesn't care which way I define it. I mean, if I choose to write the stresses and strains in this coordinate system, I mean, does the soil know the difference between that system and and this system? Did anything change when I decided that I was going to define it one way or the other? So this is a concept of a state of stress. The soil's under the same state of stress regardless of which way I define my axis system. I mean, the values are clearly going to be different in this system than the XY system. And the values of sigma A is going to be different than sigma Z. They're going to be different. But nothing's changed in the ground. The ground didn't change. Nothing changed. So that soil at A is under one state of stress, regardless of which way I write the equations, which way I define it. So the state of stress is not changing. my viewport onto that, my axis system is going to be different, and the numbers are going to be different, but it's one state of stress. So that's the concept I'm talking about that I want you to understand is we can look at things in a different way. It doesn't, and they're going to look different. It doesn't change what they are. So there's one state of stress here. And so obviously, whatever numbers I have in this particular system here, whatever numbers I have in this system here, have to be the same as, there has to be some relation to the numbers in this system because they represent the same thing. It's the same state of stress. But the numbers aren't going to be the same. But there's got to be some relationship between them. So that brings us up to the topic of stress of transforms. So we need to be able to transform our state of stress from one system to another and get the equivalent numbers in a different orientation. So let's start with in the ZX system here with our elemental area that's going to be dx by dz. This thing swipes backwards the way it makes sense to me. So we're going to have a normal stress in the z direction. We'll have sigma z. We'll have a normal stress in the x direction. It's going to be sigma x. And then we'll have our two shear stresses, tau xz and tau zx. And now what we want to do is transform that to another system. So the easiest way to do it is to slice it up. So I'm going to look at this BC plane. And we're going to start off with just one plane, and then we'll talk about the transform of the whole system. And we're just going to use equilibrium, static equilibrium to do this. So now I'm interested in what's going on in this plane BC that's at an angle theta to the Z plane. And we want to know what's going on there. So this is very simple. I have a normal vector from that surface, and then I've got a vector parallel that defines that plane. And so it should be pretty obvious that, well, this is a definition. I'm sorry, it's not in the slide. This is definition. So n is just a unit normal in that direction. So that's cosine theta times I hat plus sine theta times k hat, right? So where I and k are just the unit vectors in the xz direction. So that's just the unit vector normal. And then I want to arbitrarily pick the length of CB to be equal to 1 just because it makes life easy, because I'm going to start dividing by 1. And I have to divide by that length. And dividing by 1 is always easy. So if I do that, then the length of AB is going to be sine theta, right? And the length of AC is going to be cosine theta. So you all with me? I'm just defining the size of this little triangular element. I'm going to define the size of this triangular element here because I'm going to take these. I want to do equilibrium. I need to have forces, so I need to know the area on which all these stresses act. So I need to know the length of those. So we're going to do this thing 1 unit into the. We'll do this 1 unit into the paper. So I need to know the length of those. So that's pretty straightforward. Okay. So I now have my coordinate system in the BC system here. And we're going to do summation of forces in the normal direction in the BC, that's the n direction here, is equal to 0. So that's pretty straightforward. Let me change this to that. So sigma A times 1, so that's this stress, times 1, that's the area here. I made this 1 unit long, and into the board it's 1 unit, or into the paper it's 1 unit. So this is the force in this direction, and then I have a component from the sigma x, right? And that component is going to be sigma x times cosine theta. Cosine theta was the length of this, so that's the force acting in that direction. And then the component of that that's actually in direction is cosine. So there's 2 cosines in there. One of those cosines is the length of the element there, and the other one is the direction. You with me? Okay, and similarly, I can do the same with z. In this case, z acts on this segment here, which had a length of sine theta. We just showed that. And the component in the n direction is sine theta. And then I also have the tau zx. Now tau zx acts along the length cosine, that's this, but again it's going to have a direction now sine, and then this tau zx, it acts along a length of sine, that's this. It's really sine theta times 1. I'm leaving out the 1 in there, right? And the direction is, the directional component is cosine. So when I add that all up, I'm going to get that sigma A is equal to sigma x cosine squared theta plus sigma z sine squared theta plus 2 tau zx sine cosine. If you're with me, all I've done is done equilibrium in the normal direction to the AB plane. That's all I've done. So obviously the next thing I got to do is equilibrium in the S direction, the shear component of that. So now we're going to do summation of forces in the S direction, that's this direction, is equal to 0. Whoops. Okay, so I've got tau A, right? This stress times 1, that's the length of BC again. Notice this, that I've defined my axis system here with S down. So that's a positive, so tau A is positive. Well, that's got to be equal to, again, sigma x is going to act along the length sine. So this is the same element we had before, but now the direction component of that one's cosine, right? And similarly, sigma z acts along a length. This length here was cosine, but the directional component is opposite in the S direction, so that becomes sine. And then I have the same thing with tau. I got tau zx times cosine, that's this one. Whoops, that's this one, sorry. And that direction is cosine. And then I've got the other tau zx component, and that one is going to be sine times sine. So when I add those all together, I'm going to get that the tau in the A plane, tau A, is minus sigma x sine cosine plus sigma z sine cosine plus tau zx times cosine squared minus sine squared. That's the identity from this. I'm not going to do the little trigonometric identity there. So everybody with me? All I've done is some forces in each direction and then convert it back into stresses.
So like one of the angle is the dimensions and the other one is
right.
line, and the line is the magnitude of that.
So I should write each one of these as 1 times sine theta, where because I picked this length to be 1 unit. So at least 3 of you had that question. Only one of you was brave enough to ask it. So, do you understand what I'm doing now? I can go back and do that. You want me to go back for that slide, or yes or no? Yeah. Is everybody good with that now? That's why I defined BC to be 1 unit, because I'm multiplying by 1 and dividing by 1, and life is easy. So so this is really a force here, right? This is really, if I really want to get at, this is tau A times 1 squared. It's tau A times this length 1 plus 1 into the paper, and then I'm going to divide by 1 squared to get back to tau here, because this is a force and this is a stress. Is that clear? Okay, good question. Thank you. Okay, well so I can do this. These are all these numbers, and obviously that's a lot of algebra. So what do we do in math when we got lots of algebra and it's all linear? We write it as matrices, right? So that's what we're going to do next. We're just going to turn this into a matrix operation. So if I write it in matrix form, right, I can write that sigma A is this was my x. This is my xz tensor, right? This was the xz tensor. And these are what we just call the direction cosines. I mean, one of them is sine, but they're the unit directions in the angle theta, right? That's just it's just cosine theta and sine theta. They're called the direction cosines, so the number is less than 1. And all I have to do is take this direction cosine vector and pre and post multiply it This is actually the transform of this, right? So I'm just going to take this vector, I'm going to transform it, and I pre and post multiply on the original tensor, and I'm going to get the sigma A, and I can do the same thing with the other direction cosines, which is the ones for the tau in the s direction, and I'm going to get tau A. Right? And I can do the same thing, and then the easiest way, the matrix algebra way to write that is that I'm going to take my direction cosine vector here, L1, and here's my original stress tensor in the xz direction, and multiply L1 times S, and then, that's a matrix multiplication, and then L transform, and that's going to come out to be and this is now, and that's sigma A, right? And then similarly, I can write that tau A is going to be L2 times the same stress tensor, pre-multiplied by L2 transform. But these are vector forms right now. So all I did was take all that algebra in the previous slides and write it in vector form. Everybody good with that? You don't have to really. We're not going to do a lot of vector calculus or vector algebra here, but I'm going to show it to you. I'm not going to have you doing this stuff in the exam, I promise you. Okay, so let's look at this thing in 2 dimensions then. So we were just looking at one plane before. Now let's look at the whole. We want to rotate the whole thing. That we just showed how you can calculate the stresses on one plane, but we actually want to rotate the whole axis system. So we're going to rotate this from the xz system to the 1-2 system here. Is that clear what we're doing now? So if I do that, and I'm just going to do this intuitively, we're not going to show this, I'm going to end up with, instead of a direction cosine vector, I'm going to have a direction cosine matrix, because this is a 2-by-2 transform. And instead of just producing a single value on the left-hand side, I'm going to produce my new stress tensor. So this is my input tensor, right? And this is going to be my output tensor. And I'm going to multiply by the direct. This again is going to be the direction cosine. This is now a matrix, and this is just a transform of that matrix. So if I write it in linear algebra terms, it's just the one difference between this and then the last one is these are now matrices, not vectors, and I'm producing another tensor instead of just a single value. And that is the 2-dimensional stress transforms. And so we call the L1, we call this transform matrix the direction cosine matrix. It's usually just written L1, L2, M1, M2, and it's just a combination of cosines or sines times the rotation angle. Okay. So what does it look like in 3 dimensions? Well, in 3 dimensions, we just have a 3-by-3 matrix. I mean, this is the beauty of linear algebra, right? We're gonna end up with this simple equation right here. Well, in 3 dimensions, it's the same equation. Now, when you go to actually do the work, it's a lot hairier. You got 3 sets, but it's just a 3-by-3 matrix, right? And the equation's exactly the same, except now we got a 3-by-3, and now I got 3 different angles now. But the direction cosines are the cosine between the unit, the normal vector, and you have to cross multiply the normal vector with the normal vectors in the 2 different directions to get the cosine. So it's a little more complicated mathematically, but conceptually it's just one more dimension. So, and now we have a direction cosine matrix now that's a 3-by-3, and we use L, M, and N for those ones conventionally. So we're going to use this nice, handy, short notation when we talk about it conceptually. And the few occasions that you're actually going to do the calculations, we're only going to do it in 2 dimensions, so it's not too hard. And you're going to actually have to figure out the cosines and sines. And then we'll talk in just a minute about a graphical tool for doing that. So similarly, we can transform the strains in the same way. The transform and now we have. Shouldn't have used S for this. I guess I should have used a different term for this. But these are now the strain tensors and not the stress tensors. But the direction cosine matrix is exactly the same because it's doing the same transform. It's just transforming strains instead of stresses. So the direction cosine matrix is the same. It's just that the values in here are going to be different. So obviously you're going to have different values over there. So no difference between that. And that is stress transform. So it's pretty simple. The concept is pretty simple, I think.